Hello, in today's video we're going to be talking about atomic radius. And we're going to be discussing a few experiments that were used in order to determine what the atomic radius was or is for every atom on the periodic table. Now we're not going to go through every atom, but we're going to go through a few examples of how we calculated the atomic radius. So let's first take a metal. Metals have a unique structure when they form a crystalline structure. They're regular arrays. What that means is they are periodically replicated in three-dimensional space. The X, Y, and Z axis, they're all periodically replicated in all three of those axes. So let's take an example. Let's take just a random metal. The way that the atoms would line up would look something like this. And it would go off all the way across here, up, down, out of the screen, and we would have a regular array of these atoms. Now, in order for us to determine what the radius is here, since we don't really know where the electrons are, that's going to become difficult. So the way that we've gotten around this problem is we've developed machines and instrumentation that can determine the distance between the nuclei. So you go into a laboratory and you calculate the distance between these nuclei. And let's say for this metal, we're going to get distance between the nucleus is 266 picometers. Okay. For a metal, we've assumed that the shells of the metal do not overlap. Remember, metal-metal interactions, there is no overlapping. This isn't a covalently bonded system. So what we can do in order to find the radius of a certain atom, this part, we can take the total distance between the nuclei, 266 picometers, and we can just simply divide by 2. This gives us 133 picometers. So we can do this in laboratory. There's no problem with doing this in laboratory. And that's how we've determined the atomic radius of the metals on the periodic table. We put the metal in a periodic array. We determine the distance between the nuclei. We take that distance and divide by 2, and we call it good. This is what would be put on your periodic table, the atomic radius. So that's for a metal. Now let's look at a covalently bonded system, which is slightly different. We know that in covalently bonded system, we have the sharing of electrons. So we can't really just say that the atoms are not penetrating each other. So what we're going to do is we're going to see, let's say we have a covalently bonded system of chlorines. These are both chlorines, Cl2. There's this overlap barrier here. So that makes it a little bit more difficult, makes it a little bit more tricky. We don't know where this atom ends and this atom begins. So what we can actually how we can look at this is we can redraw this with a line that looks something like this. The nucleus is in the center. And we have our new covalently bonded system here. Now we can do the same type of thing that we did before. We can go into laboratory. We can measure the distance between the nuclei. And in this case, we're going to say it's approximately 200 picometers. And now, in order to find the distance, since it gets chopped off here, it's penetrating, in order to find the distance here, we're really going to be trying to find the distance to the outer shell, as big as this thing can be for the atomic radius, because we know that it overlaps. So really, we're trying to figure out this part. Well, we can't do that quite right. We don't know how much of the electrons are shared. So we're going to do the exact same thing we did with the metal. We're going to take the total, in order to find this distance, we're going to take the total distance between the nuclei, and we're just going to divide by 2. Equals 100 picometers. So really, this is kind of like a fudge factor. We don't really know how much of the electron is being shared and how much is not being shared. So we're going to call this the atomic radii of a covalently bonded system. Now, there are a lot of combinations that are out there in the world. Lots and lots and lots. And we have atomic radii for all of the atoms. However, at the beginning, we didn't know what the atomic radii were for given atoms, or we didn't know how much of the sharing aspect was happening in the covalently bonded system. So what we can do is we can look at an example between a carbon and a Cl. We're going to have this sharing going on. The chlorine is going to be much larger than the carbon, and we have a sharing that looks like this. There's some sort of sharing going on between them. Again, we already know what the distance is for the atomic radius of chlorine. We measured that before. That was 100 picometers. We don't, let's say in this case, we don't know what this is. We don't know what the atomic radius is for carbon, so we're going to put a question mark. But we can then go into laboratory. We can measure the distance between the two nuclei. And in this case, let's say it's 177 picometers. So now we have three different variables. We have one of them that is unknown. We can set up a simple equation. The total distance, distance between the nuclei is equal to the atomic radius of carbon plus the atomic radius of chlorine. We just plug in our values. 177 picometers is equal to the atomic radius of carbon plus 100 picometers. We knew this from a previous problem. So this would be given to you if this was a problem on a quiz or an exam. And we could solve for the atomic radius of the carbon in this interaction is just going to be 177 minus 100, which is 77 picometers. And this is how we can determine what the atomic radius is for a given interaction. If we know one of them, we can call that good in this interaction, and we can solve for the unknown. So this is how we found a lot of the atomic radii on the periodic table, a lot of the radii in covalently bonded systems as well. So with that, I want to stop this video. In the next video, we're going to be talking about size differences and what affects the sizes of atoms. So really, this is going to be kind of the most difficult equation that we're going to come across for the rest of the semester. There may be a few other little equations, but really we're just going to be adding and subtracting for the rest of the semester. So with that, have a great night. I will see you all in class tomorrow.